Hello and welcome to another calculus lesson in Chapter 8, 8.3 Properties of Planes. So we're going to start by remembering some of the stuff we covered in the previous sections in this chapter. So first things first, the equation ax plus by plus c is equal to 0. So if we remind ourselves, this here is the scalar equation of a line. So we saw that. We also saw the vector equation of a plane last time, and it looked something like this. R is equal to R0 plus TA. Actually, maybe I'll stop there for a second just to point out that if I was to just stop there, this would be the vector equation of a line, because I have a position vector going to that line. So that means you know a point on the line. And also the A tells you that you're moving along the line. So that's your direction vector. And the t is some scalar multiple of that direction vector. Now, in order to have a plane, what we saw last time is that you have to add another direction vector. A line is considered one-dimensional in math, and the plane is two-dimensional. So in order to express something two-dimensional, you need two vectors that are not parallel to each other in order to span the two-dimensional space. So this here is the vector equation of a plane. Okay, now that's what we saw before. Now this here is the new equation. You were exposed to it last time, but nonetheless here it is again. Ax plus by plus cz plus d is equal to 0. This here, while it kind of looks like the scalar equation of a line just with an extra piece to it, we have to be careful not to mistakenly call this the scalar equation of a line in R3. While this is the scalar equation of a line in R2, this is not the scalar equation of a line in R3. In fact, I mentioned last time, and you probably saw in the homework as well, there is no such thing as a scalar equation of a line in R3. Okay? This here is the scalar equation of a plane. Okay, now there's a couple things. All we need to do in order to determine this equation for a plane, which is going to be what the main focus of this lesson is about, all we need to know is a point on the plane and a normal vector to the plane. Okay, so what is a normal vector? Those of you that studied physics with me, and of course if you studied the previous sections of this chapter, you would have seen that the word normal means perpendicular. There's three different words we use for at 90 degrees. Perpendicular, normal, and orthogonal. So if this here is my plane, again, imagine a plane just like a flat sheet of paper. Then a normal to the plane might look something like this. Okay, so I'm drawing this little box here to indicate that it's perpendicular to the plane, and I'm going to call this n. Usually planes are denoted with the symbol pi, so like plane 1 would be pi 1, plane 2 would be pi 2, just as lines are L1, L2, planes are pi 1, pi 2. We don't really need to worry about that right now. We'll get more into that in later sections in this chapter. Okay, so there is a derivation for determining where this equation comes from. If you're interested to see it, let me know and I can show you that derivation. But that's what we're going to be focusing on here. Now, what's really interesting here is how we get the equation for the normal. In order to understand where that comes from, you have to remember something that we covered in section 8.1. So let me do another recall here. Recall, in 8.1, you saw the following. We said that if we have a line, L, then you can determine what the normal is to that line. Again, it's perpendicular, so there's my n. And then we said, consider that the line is expressed by the equation ax plus by plus c is equal to 0. So this was the equation in standard form. And through a series of rearranging this and isolating for y, we ended up with y is equal to negative a over b x minus c over b. And so we saw that the slope of the line was negative a over b. Okay, so if the slope of the line is negative a over b, then the slope of the normal vector has to be the negative reciprocal of that. And so we saw that the negative reciprocal of negative a over b, you flip it, it's going to be b over a, and then, well, negative b over a, you take out the minus sign and it's positive b over a. And then you just have to remember that with slope, the numerator represents the rise or the y value, and the denominator represents the run or the x value. And so what we end up getting is that n can be expressed as the following vector, a comma b, which were exactly the coefficients of x and y in the standard equation for this line. Okay, so whatever the coefficients are for x and y, a and b in this case, that makes up the normal vector. And we're going to use the same idea here. So here we have my normal vector. The scalar equation of the plane is given by ax plus by plus cz plus d is equal to 0. Now, as opposed to 8.1 where we had the line in R2, this time we have this n value. It's in R3 in the third dimension. So this normal is going to be represented by, just like before, the coefficients of x, y, and now z. So it's given by a comma b comma c. And really that makes it so easy. Now, why is that necessary? So if you have some kind of a flat surface, so I'm just going to use this little post-it pad from Office Depot. If I have this little post-it pad and I have a little, let me use a paper clip here to indicate the direction. Okay, so I have this paper clip, it's perpendicular to the post-it note. Now, however I orient this plane in three-dimensional space, whether it's oriented like this, or like this, or like this, that paper clip will always be perpendicular to the plane. So however I orient it, that paper clip, whatever direction it's going in, it can identify to me how the plane is oriented in three-dimensional space. So this is why there's only two things we need to have in order to identify the plane. Like I said before, we need a point on the plane and a normal vector to the plane. And that normal vector, once you have the scalar equation of the plane, it's done. All right. So let's move on to the first example. All right, so example 1, consider the plane that has normal vector n, which is 3 minus 2, 5, and contains the point P0, which is 1, 2, negative 3. Remember, points are given by round brackets, vectors are given by square brackets. Okay, part A, write the scalar equation of the plane. Okay, so remember, vector equation, we did that last time. That was this equation. Scalar means that one right there. Okay, A with the A, B's, and C's. All right, so first thing I like to do is always say what the general equation is. I know that the general equation for the scalar equation of a plane should look something like this. AX plus BY plus CZ plus D is equal to 0, with the A, B, and C values being determined by the normal vector. The normal vector is given by A comma B comma C. Well, guess what? I have the normal vector. It's right there, 3 minus 2, 5. And so I know A, B, and C. Okay, so what that means is I'm going to plug those numbers in here. So 3x minus 2y plus 5z plus d is equal to 0. And so all that you need to find now is d. You've pretty much got the equation. And just like any equation that you need to determine one more piece of information to, you usually just need a point, and there it is. P0, 1, 2, comma, negative 3. And those are the x, y, and z values respectively. So here I go. So 3 times 1 minus 2 times 2 plus 5 times negative 3 plus d is equal to 0. Okay. So 3 times 1, that's 3. 2 times 2, that's 4. So 3 minus 4, and then minus 15 plus d is equal to 0. Okay, so 3 minus 4 is negative 1. Minus 15, that's negative 16. So negative 16 plus d is equal to 0. Rearranging that for d, you're going to get d is equal to 16. Okay, so therefore, the equation of the plane is this with d is equal to 16. So 3x minus 2y plus 5z plus 16 equals to 0. You have to have that equal sign there. Excuse me. Is the equation of the plane. Okay, so there's our final answer to the first example, part A. Hopefully that's okay so far. All right, part B, so moving on. Is vector A, which is equal to 4, 1, negative 2, parallel to the plane? Okay. The more we get into this, I guess, chapter, the more you're going to realize that there are multiple ways to solve a lot of these problems. And while there are multiple ways to solve them, that doesn't mean that the way you're doing it is necessarily wrong, but there are incorrect ways of doing it too. So just be careful and make sure that what you're doing uses the correct logic and the correct concepts. For this kind of a question, you got to visualize it. So we've got a vector. We want to know if it's parallel to the plane. So just sketch a plane. I cannot emphasize this enough. Draw a picture. It'll help you visualize the situation. Okay, so there's your plane. Your normal vector looks something like this. Okay, regardless, it's going to look something like that, however it's oriented. Now, if A is parallel to the plane, A might look something like this. Well, guess what? We know that the normal vector is perpendicular to the plane, and the plane is parallel to A. So therefore, normal vector must also be perpendicular to A. And just having that picture allows you to see it that much more easily. Okay, so we have established that A must be perpendicular to the normal vector. So therefore, well, what do we know? When two things are perpendicular, we automatically think that their dot product is 0. And sure enough, that's going to help us here. Okay, so therefore, A dot n is 0. All right, so here's how we're going to check. We have A, we have n from the previous part, right? So there's your value for n, 3 minus 2, 5. So going back here, so 4, 1 minus 2, dotted with 3 minus 2, 5. We have to check what this is equal to. All right, so 4 times 3 plus 1 times negative 2 plus negative 2 times 5. All right, 4 times 3 is 12. 1 times negative 2 is negative 2. Negative 2 times 5 is negative 10. Okay, 12 minus 2, that's 10. 10 minus 10 is 0. Perfect. Okay, so since the dot product is 0, okay, so therefore A is parallel to the plane. And then we can just put here, since A dot n is equal to 0. Okay. Hopefully that's all right. Okay, so moving on to part C. Is vector B normal to the plane? Vector B is 15, negative 10, 25. Okay, so again, quick sketch. There's your plane, there's your normal vector. If you have this kind of scenario, we're trying to see if B is normal to the plane, that means B most likely looks something like this. Now just remember, B doesn't have to be oriented up, it could be going down. It doesn't really matter in this case, it doesn't change the mathematics, but just keep that in mind. Now, first thing I notice, okay, if B is normal or perpendicular to the plane, well, if I knew a vector on the plane, I could just take the dot product of B with that vector and show that it equals 0. Now, for those of you thinking, well, I just showed in part B that A is parallel to the plane. So maybe I could take the dot product of B with A and show that it equals 0. Okay, well, you could do that, but there's a little bit of a potential hole you could fall into here. If you made a mistake in part B and then you use that mistake in part C, you run the risk of getting very low marks on both parts of the question. So try to figure out how to solve the question without using information from previous sections, from previous results rather. Okay? So there's another way to do this. If B is normal to the plane, that means that B and N are parallel to each other. Okay, so B must be parallel to N. Now, when two things are parallel, that means they are scalar multiples of each other. So I should say if B is parallel to N, then B should be a scalar multiple of N. In other words, there should be some K value where B is equal to K times N. And we're trying to see if that's the case. Okay, so B is right there, 15 minus 10, 25. We're going to set that equal to K times N. So N is that same N value. It's 3 minus 2, 5. All right, so I mean, you can go ahead and make your 3 series of equations, or if it's fast, I mean, this one, I think you can probably just look at it and tell what the answer is going to be. You can show your work like this too. Okay, so from the x dimension to the other x dimension, it has to be the same factor. Okay, so 15 to 3, you can say, well, I have to divide by 5 or multiply by 1/5. Well, I'm just going to go the other way around because that way I'll go from smaller to bigger. So from one x dimension to the other, from 3 to 15, I know I have to multiply by 5. As long as it's the same scalar multiple for the y and z dimensions as well, that means they're scalar multiples. If even one dimension has a different scalar multiple, then it's not the case. All right, so from y to y, -2 times 5 is -10, so that's also 5. And sure enough, from 5 to 25, I have to multiply by 5. So since in every case the scalar multiple is the same, it's 5. Therefore, B is parallel to the plane. So since B is a scalar multiple of N, therefore B is parallel. Oh, sorry, not parallel. B is normal to the plane. Stick that in a box. All right, so there we go. That's part C. And we're going to move on to the last part of this example, part D. Part D says find another vector that is normal to the plane. Okay, another vector that is normal to the plane. Well, you already know that in order for a vector to also be normal to the plane, it's got to be parallel to n, right? And if something is parallel to n, that means it should be a scalar multiple of n. And so that's pretty much what we're left with here. There's a lot of different values that you could figure out for k. In fact, there are an infinite number of values you could theoretically plug in for k to get a scalar multiple of n. And so you just have to pick something that works, something simple. I'm going to let my vector be c, right? So that's my new vector, and I'm just going to let that be 2 times the normal vector. It's a scalar multiple. Okay, so 2 times n, which is 3 minus 2, 5. So that becomes 6 minus 4, 10. So there is one possible answer. Okay. We are now at this point halfway through the lesson, so let's move on to example 2. Okay, find the scalar equation of the plane containing the points A, which is -3, -1, -2, B, which is 4, 6, 2, and C, which was 5, minus 4, 1. So like I said for the previous sets of examples, in order to solve a lot of these questions, you have to use what you know use those tools and problem solve your way to figure out the answer. You have to have a very good logical and reasoning here. All right, so we have 3 points. So I'm going to sketch my plane. Again, I strongly encourage you to draw a picture. So I've got 3 points. I don't know exactly where they are, but I know I have 3 points somewhere in space, and I know they're on the plane. So I'm just going to label these points A, B, and C. Okay, all I know is that they're distinct points, and that is good enough for me. All right. In order to find the scalar equation of the line, let's just state what it looks like. I know that the scalar equation of the line should look something like this. AX plus BY plus CZ plus D is equal to 0. Now, there's a couple things I know here. In order to find A, B, and C, all I need to know is a normal vector to this plane, some vector that is perpendicular to this plane. That way I have 3 out of the 4 unknowns. And then to find the last unknown, D, all I need to do is plug in a point. And I have 3 points here. So that part will be simple. What I have to focus on here is how do I figure out a vector that's perpendicular to the plane? So if you want, pause the video and think about that for a moment. We'll resume in a minute. Okay, well, that was less than a minute, but hopefully you paused it for a minute. So here we go. We're going to see if we can figure out a normal vector to that plane. Now, a skill that you learned recently is called crossproduct. Okay, so I know that dot product, it's also known as scalar product. It returns a scalar value, just a number, but crossproduct returns a vector. And I know that when I take the crossproduct of 2 vectors, I always get a vector that is perpendicular to the original 2. And I figure out the direction of that new perpendicular vector using right-hand rule. And so, well, guess what? I have 3 points here. I can come up with 2 sets of vectors here and take their cross product. And since both of those vectors will be in the plane, that means that the cross product of those 2 vectors has to be perpendicular to the plane. Now, it's up to you how you want to combine these points to make your 2 vectors. There's a lot of different combinations you can use. Okay, so for example, one combination you could use is the vector AB and the vector AC, and you can cross those 2. You could do AB cross AC. You could do AC cross AB. It doesn't matter. Hey, you could take the vector CB and the vector CA, and you could cross them. You could take BA and BC and cross them. Either way, you have 2 vectors that are in the plane, so when you cross them, you have to get a vector that is perpendicular to both of the original ones. Okay, so let's say I want to do AC cross AB. Okay, if I do AC cross AB, that means I take my right hand, my right fingers point in the direction of that first vector there initially, and then I curl them towards the second vector. That's why I did AC cross AB instead of AB cross AC, just because I didn't want my hand oriented down as I'm trying to show you this in the camera. So AC, my fingers are pointing like this, right? So in the direction of C, and I have to curl towards AB. And in order for me to do that, the orientation of my right hand has to be such that my right thumb is pointing up. So it's perpendicular to the page, and therefore it's perpendicular to this plane. So there's my normal vector, and it's perpendicular to both of those original ones. Okay, so that normal vector I'm going to obtain by taking AC and crossing AB. So if I did AB cross AC, my normal vector would just be pointing down, but still perpendicular to the plane. Okay, so in order to take the cross product, I have to first figure out what these vectors are, and that will be simple because I already know the points. So here I go. Let's do AC first. The vector AC is going to be OC minus OA. Okay, now, the position vector OC, I know it's a position vector because I'm starting from the origin and it's going to point C. That is simply point C, but with square brackets around it. So that's going to be 5 minus 4, 1, minus OA, minus 3, minus 1, minus 2. All right. All right, so just subtract the corresponding dimensions. 5 minus negative 3, that's 5 plus 3, which is 8. Negative 4 minus negative 1, that's negative 4 plus 1, which is negative 3. And 1 minus negative 2 is 1 plus 2, which is 3. So 8, negative 3, 3. All right, so there's AC. Let's go ahead and find AB. So same way, this is OB minus OA. So that's 4, 6, 2 minus negative 3, negative 1, negative 2. All right. 4 minus negative 3, that's 4 plus 3, which is 7. 6 minus negative 1, that's 6 plus 1, which is 7. And 2 minus negative 2, that's 2 plus 2, which is 4. So 7, 7, 4. Okay, now to take the cross product. Okay, so I'm going to just move down here. So you remember how to do this. AC cross AB is equal to, so I set up my ijk twice. The first vector goes in the second row, and then the next vector goes in the third row. Okay, so AC is right here, 8 minus 3, 3. Write it twice. And AB is 7, 7, 4. Write it twice. And then what I like to do is just draw my arrows. Okay, so my diagonal arrows from I, J, and K. And then in the other direction, 2I, J, and K. I noticed some of you have preferred to memorize the formula. That's great. No problem with that. You're still going to get the correct final result. Just be careful, make sure you're using the right formula. And if you're using the formula, by the way, you gotta state the formula first in order for this to be a method of showing your work. Okay, so here we go. I know my result's a vector with x, y, and z quantities. So for x, I'm gonna have negative 3 times 4 minus 7 times 3. I'm starting to think I should have wrote this on the next line, but okay, anyways, let's go. 3 times 7 minus 4 times 8. Oh, I might fit it. 8 times 7 minus 7 times negative 3. Okay. Oh, and it's cut off there. Okay, here we go. So there's my vector. Let's compute what this is. Negative 3 times 4, that's minus 12. 7 times 3 is 21. 7 times 3, again, 21. 4 times 8 is 32. 8 times 7 is 56. 7 times negative 3, that's negative 21. So 56 minus negative 21 is 56 plus 21. All right, so I just have to figure out what that's equal to. All right, negative 12 minus 21, that's negative 33. 21 minus 32, just imagine you're doing 32 minus 21 and stick a negative sign in front. Okay, that's going to be minus 11. 56 and 21, that's what do we get? 77. Okay, I've already made the observation that these are all multiples of 11, but I'm going to just leave that for a moment. Now that I have the cross product, I know that this here is going to represent my normal vector. And there is A, B, and C, respectively. Okay, so again, remember the scalar equation for the plane looks like this. AX plus BY plus CZ plus D is equal to 0. I now have A, B, and C. Okay, I'll just write that down again. AX plus BY plus CZ plus D is equal to 0. There I go. Negative 33X minus 11Y plus 77Z plus D is equal to 0. Now last step, since I have to find D, I just need to plug in a point. And you can plug in whatever point you want. I'm just going to use B. So plug in B. B is 4, 6, 2. I just chose that because all the entries are positive. It's up to you. Minus 33 times 4 minus 11 times 6 plus 77 times 2. In retrospect, maybe I should have actually reduced this first. That would have made this calculation a bit easier, but well, we're here, so let's just go with it. All right, negative 33 times 4, so that's going to be minus 132. Negative 11 times 6, that's minus 66. 77 times 2, that is 1, 5, 4. And then plus d is equal to 0. Okay, so let's see, negative 132 minus 66. So that's going to be a larger negative number. That's going to be negative 198 plus 154. Okay, we're looking at minus 44 plus d is equal to 0. So therefore d is equal to 44. Great. Okay, so at this point we would say therefore negative 33x minus 11y plus 77z plus 44 is equal to 0. And lo and behold, all of those values are multiples of 11. So I'm going to divide left and right side by 11, and I'm going to get the reduced equation, negative 3x minus y plus 7z plus 4 is equal to 0. And this is your final answer. Now again, if you wanted to reduce it from here, actually, so I take back what I said originally, actually it would be better to reduce this originally and then work through it and figure out your d value. Okay, so that is the result for example 2. All right, we have one more example to go through, and that example has 2 parts. So this is example 3. All right, so example 3 asks us to determine the scalar equation of each plane. That's what we're all focused on today. Example 3. Okay. Determine the scalar equation of each plane. Okay, so in part A, we know that the plane is parallel to the xz plane, and it goes through the point -7, 8, 9. And so remember, a couple things you need to know in order to get the scalar equation of the plane. You got to know a vector that's normal to the plane, and you need to know a point. Okay, so I already know a point, it's given to me. That means that this piece of information right here, parallel to the xz plane, that's going to help me determine a normal vector. Okay. So first thing I'm going to do is draw a picture. So here are my coordinate axes. So x, y, and z. Now, I know that the plane I'm dealing with is parallel to the xz plane. Right, so that means it might look something like this. Okay. There is a plane parallel to the xz plane. Now, what I noticed right away is that in order for me to define a normal vector, the normal vector has to be perpendicular to this plane. So it's either going to come out over here, it might come out over here, or over here. Either way, it's perpendicular to the plane, so it's at 90 degrees. But there is a really simple normal vector that I can choose, and that is if I stick it right here. Okay, so that is a normal vector along the y-axis. And I know a really simple vector along the y-axis. It's called j hat. This is the unit vector along the y-axis direction. Of course, like I said, unfortunately, we don't use the hat symbols in high school, but you will use them next year. So we're just going to call this J010. By the way, if any of you want to use the hat symbol on your exam, you are more than welcome to. It's actually more correct to do so. All right, so I have my j hat, so 0, 1, 0, and I know that j is perpendicular to the plane. Okay, so again, here's j, 0, 1, 0. That means these represent the entries A, B, and C, since this is effectively the normal vector. So that means A is 0, B is 1, and C is 0. Right? So remember, this is effectively the normal vector. Okay, so I know the equation of my plane is AX plus BY plus CZ plus D is equal to 0. Right? So now I know A, B, and C. So 0x plus 1y plus 0z plus D is equal to 0. So that first term is gone, third term is gone. So I end up with y plus D is equal to 0. Plug in a point. Right? So it's up to you which point you want to plug in. Well, actually, sorry, no, not in this case. We only have one point. -7, 8, 9. So plug in -7, 8, 9. Now, I can only plug in one of those terms, 8, because there's no place to plug in an x or a z value. So I plug in my 8 since that's the y. So 8 plus d is equal to 0. D is equal to -8. Okay, so the scalar equation, therefore, is just y minus 8 is equal to 0. Right, because the scalar equation should have been y plus d is equal to 0. So if you find that d is equal to -8, it just becomes y minus 8 is equal to 0. So looking at that, it's interesting, because if you just saw y is equal to 8 and you didn't know what context you were in, you might think that this is just a horizontal line, so that wouldn't be a function in two-dimensional space. But sure enough, in this particular instance, this represents the equation of a plane. So therefore, this is the scalar equation of the plane. Okay, so there's part A. Let's move on to part B. Okay, so same thing, determine the scalar equation of the plane, right? So same question, determine this for this criteria. For the plane containing the line x, y, z equals 1, 2, 4 plus t times 4, 1, 11, and, oh, there we go, and perpendicular to x, y, z equals 4, 15, 8 plus s 2, 3, minus 1. Okay, so notice the second thing is also a line, right? So contains one line is perpendicular to the other. Can't emphasize this enough. Draw a picture, all right? So we have a plane, we have a line on that plane. Now, just for my own sake, I'm going to label these. So I'm going to call this first line L1, and I'm going to call this second line L2. Okay, so L1, I know it's in the plane because the plane contains this line, so I'll just draw a line in this plane. Now, this line, we have a position vector going to that line, which means that I know this point on the line. So wherever that point happens to be, I know that there is the point 1, 2, 4. And since the line is in the plane, that means that this point is also on the plane. Hence, I know a point on the plane. So therefore, a point on the plane is 1, 2, 4. That's very important because all I need now is a vector that is perpendicular to the plane. Now, this piece of information here, we can call this M1, the direction vector for plane 1. That might be going either up the line or down the line. So regardless, we don't know here, but what we do know is that it's in the plane. So that's not a normal vector. Okay. Now for L2, L2 is perpendicular to the plane. So wherever L2 happens to be, so if this is L2 and it continues down here, let's say, there is this, that's a point on L2. That doesn't really help me because it might be on the plane, but that's a very rare chance. It might be up here, it might be down here, so that's not relevant. But I know the direction vector of this line, so we'll call that M2. Excuse me. So M2 is either going to go up or it might go down, but regardless, whether it goes up or down, it's perpendicular to the plane. Hence, it can act as a normal vector for the plane. So since L2 is perpendicular to the plane, M2 can act as n, which is the normal vector. So therefore n, we can just call it this, 2, 3, -1. All right, so once you have your normal vector, you know the values of a, b, and c for the scalar equation of your line. Right? So we know that, scalar equation of the plane, ax plus by plus cz plus d is equal to 0. So there it is. Always state that first. All right, so now we have 2 for A. We have 3 for Y and minus 1 for C. Okay. So there we go. All that's left to do is figure out what that capital letter D is, and we do that by using the point. So we're going to take that point, plug it in for X, Y, and Z. So 2 times 1 plus 3 times 2 minus 4 plus D is equal to 0. So 2 plus 6 minus 4 plus D is equal to 0. 2 plus 6 is 8, minus 4 is 4. So 4 plus D is equal to 0, which means D is equal to negative 4. So therefore, the equation of the plane is so it starts from here, right? 2x plus 3y minus z plus d when d is minus 4. So minus 4 is equal to 0. Okay, so that is the end of lesson 8.3, properties of planes. So please remember, a very important piece of information for this lesson is you gotta problem solve. You gotta draw a picture. So just doing this is showing a tremendous amount of work for this question. If you don't draw a picture, first of all, you run the risk of making a very simple mistake that will compound later on. And second, you have to show work in some other way. Okay, so simply ignoring the picture and writing everything else is not sufficient. Include this, demonstrate to me that you could understand what's going on. So practice this in your homework, and of course there will be some tasks coming up that also help you to demonstrate these skills. All right, so again, that is the end of video 8.3. Stay tuned next time for video 8.4.